We have now seen that we can produce hydrogen and oxygen from the water that we obtained from the candle. Hydrogen, you know, comes from the candle, and oxygen, you believe, comes from the air. But then you have a right to ask me, how is it that the air and the oxygen do not equally well burn the candle? If you remember what happened when I put a jar of oxygen over a piece of candle, you recollect that there was a very different kind of combustion to that which takes place in air. Why is this? It's a very important question, and one I shall endeavor to make you understand. It relates most intimately to the nature of the atmosphere, and it's most important to us. We have several tests for oxygen besides the mere burning of bodies. You've seen a candle burnt in oxygen or in the air, but we have other tests beside these, and I'm about to show you one of them for the purpose of carrying your conviction and your experience further. It's a very curious and useful one. I have here a flask half filled with a solution of potassium hydroxide, glucose, and methylene blue indicator, and filled the rest of the way with oxygen gas. I shake the flask and the oxygen mixes with the solution. What happens, say you? They together produce no such combustion as was seen in the case of the candle, but see how the presence of oxygen is told by its association with these other substances. What a beautiful colored solution I have obtained in this way, showing me the presence of the oxygen. In the same way, we can try this experiment by mixing common air with this solution. Here's another flask containing the same solution, but this time with air above it. I shake this flask and you see the result. The solution turns blue, and that shows me that there's oxygen in the air, the very substance that had been already obtained by us from the water produced by the candle. But then, beyond that, how is it that the candle does not burn in air as well as in oxygen? We will come to that point at once. The solutions react with the gas, and the appearance to the eye is alike in both, and I cannot tell which of these flasks contains oxygen and which contains air, although I know they have been previously filled with these gases. In order to examine whether there is any difference between them, we simply need to wait. Notice how the blue color of the solution fades in this flask, the flask with air. Why is that? Because there is in air, besides oxygen, something else present. The solution left something untouched. There is in fact a gas in air which the solution cannot touch, and this gas is not oxygen and yet is part of the atmosphere. So that is one way of opening out air into the two things of which it's composed. Oxygen, which burns our candles or anything else, and this other substance, nitrogen, which will not burn them. This other part of the air is by far the larger proportion, and it's a very curious body when we come to examine it. It is remarkably curious, and yet you say perhaps that it's very uninteresting. It is uninteresting in some respects because of this, that it shows no brilliant effects of combustion. If I test it with a taper as I do oxygen and hydrogen, it does not burn like hydrogen, nor does it make the taper burn like oxygen. It has no smell, it is not sour, it does not dissolve in water, it is neither an acid nor an alkali. It is as indifferent to all our organs as it is possible for a thing to be. And you might say, it is nothing. It is not worth chemical attention. What does it do in the air? Then come our beautiful and fine results shown us by an observant philosophy. Suppose in place of having nitrogen or nitrogen and oxygen, we had pure oxygen as our atmosphere. What would become of us? A piece of iron lit in a jar of oxygen, for example, goes on burning to the end. When you see a fire in an iron grate, imagine where the grate would go if the whole of the atmosphere were oxygen. The grate would burn up more powerfully than the coals, for the iron of the grate itself is even more combustible than the coals which we burn in it. A fire put into the middle of a locomotive would be a fire in a magazine of fuel if the atmosphere were oxygen. The nitrogen lowers it down and makes it moderate and useful for us, and then with all that, it takes away with it the fumes that you have seen produced from the candle, disperses them throughout the whole of the atmosphere, and carries them away to places where they are wanted to perform a great and glorious purpose of good to humankind for the sustenance of vegetation. and thus does a most wonderful work. Although you say on examining it, why, it is a perfectly indifferent thing. This nitrogen in its ordinary state is an inactive element. No action short of the most intense electric force, and then in the most infinitely small degree, can cause the nitrogen to combine directly with other elements of the atmosphere or with other things round it. It is a perfectly indifferent, and therefore to say, a safe substance. But before I take you to that result, I must tell you about the atmosphere itself. Here is a composition of 100 parts of atmospheric air. It is a true analysis of the atmosphere, so far as
It's crazy to think that these are Faraday's lectures. Like he knew this much about like the atmosphere in chemistry in 1861. It's really cool.
regards the quantity of oxygen and the quantity of nitrogen present. By our analysis, we find that 5 liters of the atmosphere contains only 1 liter of oxygen and 4 liters of nitrogen by bulk. That is our analysis of the atmosphere. It requires all that quantity of nitrogen to reduce the oxygen down so as to be able to supply the candle properly with fuel, so as to supply us with an atmosphere which our lungs can healthily and safely breathe. For it is just as important to make the oxygen right for us to breathe as it is to make the atmosphere right for the burning of the fire and the candle. First of all, let me tell you the weight of these gases. 2 liters of nitrogen weighs roughly 2.29 grams. The oxygen is heavier. 2 liters of it weigh about 2.62 grams. 2 liters of air weigh about 2.37 grams. You might ask, how do you weigh gases? I will show you. It's very simple and easily done. Here is a balance, and here is a plastic bottle. This bottle is balanced by the weight of the other bottle. And here is a pump by which we can force the air into the bottle, and with it we will force in a certain number of volumes of air. Now, see how it sinks? It is much heavier than it was. By what? By the air that we have forced into it by the pump. There's not a greater volume of air, but there is the same volume of heavier air because we have forced in air upon it. This bulk of air weighs about 2.5 grams. It is wonderful how it accumulates when you come to larger volumes.
Isn't that wrong? Isn't there a greater volume of air? Isn't there a greater volume of air? He pumped in more air. Yeah, there's more volume. It's not heavier air, it's more... We have forced more air in it, so there's not heavier air, there's just a greater volume of air.
I have calculated the weight of air in this room, and you would hardly imagine it, but it is above a ton. So rapidly do the weights rise up, and so important is the presence of the atmosphere, and of the oxygen and the nitrogen in it, and the use it performs in conveying things to and fro from place to place, and carrying bad vapors to places where they will do good instead of harm. Having given you that little illustration with respect to the weight of the air, let me show you certain consequences of it. When I put my finger on this tube and remove the air, look at what happens. Why is my finger fastened to this tube, and why am I able to pull the hose about? It is the weight of the air that is above. I have another experiment here which I think will explain to you more about it. When air is pumped from underneath the plastic, which is stretched over the funnel, you will see the effect in another shape. The top is quite flat at present, but it will make a very little motion.
Because it's like Faraday didn't have plastic back in his day. So... yeah.
Motion with the pump, and now look at it. See how it has gone down, and see how it's bent in? You will see the plastic go in more and more until at last I expect it will be driven in and broken by the force of the atmosphere pressing upon it. Now, that was done entirely by the weight of the air pressing on it, and you can easily understand how that is. The particles that are piled up in the atmosphere stand upon each other as these 5 cubes do. You can easily conceive that 4 of these 5 cubes are resting upon the bottom one, and if I take that away, the others will all sink down. So it is with the atmosphere. The air that is above is sustained by the air that is beneath, and when the air is pumped away from beneath them, the change occurs which you saw when I placed my finger on the air pump and which
Vacuum seals happen because of air pressure. Can you make vacuum seals in space? Does that do anything? Like, would that plastic pop in space? It's a question for NASA.
which you saw in the case of the plastic and which you shall see better in the next demonstration. It's a little apparatus of 2 hollow plastic hemispheres closely fitted together and having an outlet through which we can exhaust the air from the inside. And although the 2 halves are so easily taken apart while the air is left within, yet you will see when we exhaust it by and by, I'll be unable to pull them apart. And if I take that away, the others will all sink down. So it is with the atmosphere. The air that is above is sustained by the air that is beneath, and when the air is pumped away from beneath them, the change occurs which you saw when I placed my finger on the air pump and which you saw in the case of the plastic and which you shall see better in the next demonstration. It's a little apparatus of 2 hollow plastic hemispheres closely fitted together and having an outlet through which we can exhaust the air from the inside. And although the 2 halves are so easily taken apart while the air is left within, yet you will see when we exhaust it by and by, I'll be unable to pull them apart. Every square inch of surface that is contained in the area of this vessel sustains 15 pounds by weight, or nearly so, when the air is taken out. Here is another very pretty thing, a suction cup. If I clamp it upon the glass, you can see at once it holds. I can easily slip it about, and if I pull it up, it pulls the glass plate with it. Only when I lift the edge can I get it off. Why does it hold? It is only kept down by the pressure of the atmosphere above. I have a second one, and if I press them together, you'll see how firmly they stick. And indeed, we may use them as they are proposed to be used, to stick against windows or against walls, where they will adhere for an evening and serve to hang anything on them that you want. Next is an experiment that you can do at home. It is a very pretty illustration of the pressure of the atmosphere. The pop gun will confine the air that is within the tube perfectly and completely for our purpose. The confined air will drive the front ball out with a force something like that of gunpowder, for gunpowder is in part dependent upon the same action as this pop gun. I saw the other day an experiment which pleased me much, as I thought it would serve our purpose here.
Yeah, but it is volume dependent for this pop gun, you know.
By the proper application of air, I expect to be able to drive this egg out of one cup into the other by the force of my breath. But if I fail, it's in a good cause, and I do not promise success because I've been talking more than I ought to make the experiment succeed. You see that the air which I blew went downward between the egg and the cup and made a blast under the egg, and is thus able to lift a heavy thing, for a full egg is a very heavy thing for air to lift. If you want to make the experiment, you'd better boil the egg quite hard first, and then you may very safely try to blow it from one cup to the other with a little care. I have now kept you long enough upon this property of the weight of the air, but there's another thing I should like to mention. You saw the way in which the pop gun, I was able to drive the second yellow ball a half or 2/3 of an inch before the first ball started by virtue of the elasticity of the air. Just as I pressed into the plastic bottle the particles of air by means of a pump, now this depends upon a wonderful property in the air, namely its compressibility. And I should like to give you a good demonstration of this. If I take anything that confines the air properly, as does this balloon, which also is able to contract and expand so as to give us a measure of the elasticity of the air, and confine in the balloon a certain portion of air, and then if we take the atmosphere off with this pump, just as in the cases we put the pressure on, if we take the pressure off, you will see how it will then go on expanding and expanding larger and larger until it will fill the whole of this jar. We will now turn to another very important part of our subject, remembering that we have examined the candle in its burning and have found that it gives rise to various products. We have the products you know of soot, of water, and of something else which you have not yet examined. We have collected the water, but have allowed the other things to go into the air. Let us now examine some of these other products. Here is an experiment which I think will help you in part in this way. First, we put our candle under a chimney. My candle will go on burning because the air passage is open at the bottom and at the top. You see the moisture appearing, that you already know about. It is water produced from the candle by the action of the air upon the hydrogen. But besides that, something is going out at the top. It is not moisture, it's not water, it is not condensable, and yet, after all, it has very singular properties. You will find that the gas coming out of the top of our chimney is nearly sufficient to blow the light out I'm holding to it. And if I put the light fairly opposed to the current, it will blow it quite out. You will say that that is as it should be, because the nitrogen does not support combustion and ought to put the match out, since the match will not burn in nitrogen. But is there nothing else there than nitrogen? I must now anticipate. That is to say, I must use my own knowledge to supply you with the means that we adopt for the purpose of ascertaining these things and examining such gases as these. If I hold an empty flask to this chimney, I shall capture the combustion of the candle below. We shall soon find that this flask contains not merely a gas that is bad as regards the combustion of a taper put into it, but having other properties. If I take some of this beautiful, clear lime water and pour it into this flask which has collected the gas from the candle, you will see a change come about. You see that the water has become quite milky. Observe, this will not happen with air merely. Here is a flask filled with air, and if I put a little lime water into it, neither the oxygen, nor the nitrogen, nor anything else that is in that quantity of air will make any change in the lime water. It remains perfectly clear. And no shaking of that quantity of lime water with that quantity of air in its common state will cause any change. This is chalk consisting of the lime in the lime water combined with something that came from the candle. That other product which we are in search of and which I want to tell you about today. This is a substance made visible to us by its action, which is not the action of the lime water either upon the oxygen or upon the nitrogen, nor upon the water itself, but it is something new to us from the candle. But we have a better means of getting the substance and in greater quantity so as to ascertain what its general characteristics are. We can produce this substance in great abundance from a multitude of unexpected sources. All limestones can produce a great deal of this gas, which issues from the candle, and which we call carbon dioxide. All chalks, all shells, all corals can also make a great quantity of this curious gas. We can easily evolve carbon dioxide from marble. Here is a jar containing some hydrochloric acid, and here's a taper which, if I put it into that jar, will show only the presence of common air. There is, you see, pure air down to the bottom. The jar is full of it. Here is a substance, marble, a very beautiful and superior marble, and if I put that piece into the jar, a great boiling apparently goes on. That, however, is not steam. It is a gas that is rising up. And if I now search the jar by a taper, I shall have exactly the same effect produced upon the taper as I had from the gas which issued from the end of the chimney over the burning candle. It is exactly the same action and caused by the very same substance that issued from the candle. And in this way, we can get carbon dioxide in great abundance. We have already nearly filled the jar. We also find that this gas is not merely contained in marble. Here is some common chalk, and in this flask, more hydrochloric acid. It too evolves carbon dioxide, exactly the same in its nature and properties as the gas we obtain from the combustion of the candle in the atmosphere. And no matter how different the methods, from marble or chalk or candle, by which we prepare this carbon dioxide, you will see when we get to the end of our subject that it is all exactly the same whether prepared in the one way or another. We will now proceed to the next experiment with regard to carbon dioxide. What is its nature? Here is a vessel full of carbon dioxide, and we will try it, as we have done in so many other gases, by combustion. You see, it is not combustible, nor does it support combustion. Neither, as we know, does it dissolve much in water, because we collect it over water very easily. Then you know that it has an effect and becomes white in contact with lime water. And when it does become white in that way, it becomes one of the constituents to make carbonate of lime or limestone. It is a very weighty gas. It is heavier than the atmosphere. I have put their respective weights at the lower part of this table, along with, for comparison, the weights of the other gases we've been examining. 2 liters of this weighs about 3.6 grams. You can see by some experiments that this is a heavy gas. I have a flask containing dry ice that is subliming and thus pushing out the air, replacing it with carbon dioxide. I'll pour a little of this carbon dioxide into another flask filled with nothing but air. I wonder whether any has gone in or not. I cannot tell by the appearance, but I can in this way. It extinguishes the flame. If I were to examine it by lime water, I would find it by that test also. Next is an experiment where I will show you its density. If I blow soap bubbles, which of course are filled with air, into this container filled with carbon dioxide, they will float. They are floating by virtue of the greater density of the carbon dioxide than of the air. And now, having so far given you the history of carbon dioxide as to its sources in the candle, as to its physical properties and density, in the next lecture I shall show you of what it is composed and where it gets its elements from.